search. So, so we had, last time we had gone over this parentheses theorem of depth first search, which said that if you have any two vertices u and v, you look at their discovery times and finish times, then they sort of make a parenthetical statement, right? So you have case 1 or case 2, which is effectively the same. That is the discovery interval, or the interval that sort of u is alive or u is active in DFS is a subset of v's interval or vice versa. And in case 3, they're basically disjoint. You never have a situation like this, right, where the intervals overlap. And this is just a consequence of it being on a stack. Okay? Is that any questions? Is that clear? Good. Note that if things are in a queue in BFS, things can look like that. Like both these things are on the queue, and then U exits the queue first. Right? It's going to look a lot like that if you think about BFS. Okay, so what is the utility of doing this sort of exercise? Or what is the utility of having these definitions? Is the applications that we'll talk about today are on topological sort and DAGs. So what is a DAG? A directed acyclic graph, if G is a directed graph and contains no directed cycles. So a cycle of this form, right? 1 goes to 2, which goes to 3, which goes to 4, and back to 1. That is a cycle. So a DAG contains no such cycles. So this is not a directed cycle. Because although the edges in the undirected world form a cycle, in the directed world they don't. Why would you want to check if something is a DAG? So an example, a classic example is compilers. So let's just say that each vertex over here is a file. And there's an edge if there's a dependency between the files. So in this case, you have an edge from this file bar.c, or rather from foo.c to bar.c, because this edge says, compile this first before you compile this. Right? Because essentially there's a hash include. So compile foo.c before you compile bar.c, so on and so forth. Make sense? And so what I'm going to show you today is that given a graph, how do you determine if it's a DAG or not? Right? And really you should think of this just like this example with this coactor graph. There's a huge data set. There's just a file that says, this depends on this depends on this depends on this, so on and so forth. How do you determine if you actually get a DAG from it? If it forms a DAG. And so depth first search gives you a linear time algorithm. It gives you an O of m plus n time algorithm because you can run one depth first search and you can determine this answer. Okay? The second thing we will discuss is topological sorting. So what is topological sorting? It says given a DAG, I put in quotes, sort the vertices in DAG order. So what this means is you label the vertices v1 to vn so that for all edges, the edges go from lower in the order to higher in the order. So you can think of this as like you basically put down the vertices in a list and the edges go from lower in the list to higher in the list. You don't actually have to change the labels explicitly. Yeah? Well, why they call this topological sort? I mean, okay, you mean why do they call it topological? Topology, I mean, so sometimes the connections of a graph, like a graph is supposed to be like a topological representation of things. So that's one of the reasons why they use this term. In the networks literature, like the computer networks literature, they'll often talk about their network topology, which basically just means network graph. So you can think of this as like graph sort. But the term that is often used is topological sort. So like if it came up in an interview or something like that, you would say topological sort. So I want you to know that term because that's it's like a kind of question you could be asked about. Like in an interview, like, oh, you have these files, how should you compile them? You should say DAG, topological sort. They'll probably give you the job. Yeah. But it has nothing to, well, It kind of sort of has to do with the mathematical field of topology because sometimes they use graphs to represent certain surfaces. But in this case, I think topology is more just used like graph. Okay, so we discussed the topological ordering of a graph is unique. That is false. But there do exist graphs where the topological ordering is unique, so there's that. So the two questions that we want to ask is, given a DAG as an adjacency list, find a topological ordering, which we can do with DFS. And given the adjacency list of G, determine if G is a DAG. So this is the basic question, and the next one is the more advanced one. And the beauty of DFS is that DFS gives actually a remarkably simple solution to both these problems. Okay, so how are we going to do this? So let's look at the first question. I'm just going to run DFS on G. Now remember, we discussed that the actual forest that you get depends on the labels. It depends on the labels, it depends on how you sort, like how the labels are ordered. So if you remember, when I run DFS of G, I have this for loop here, but this could be ordering in, we don't know what ordering it is, right? And so that is the challenge in understanding depth first search. So now let me ask you, okay, so first, when you run DFSG, we get the DFS forest, and these are all basically, you can think of predecessor U edges. Right, so the DFS forest is going to give you some structure. These are not necessarily connected components because you could have an edge. There could be an edge like this in the actual graph. Is that clear? There could be an edge like that in the graph. So the graph could actually be, so the graph is this huge thing. These are just the tree edges. There could be an edge like that in the graph. Yes?
You said these are not necessarily connected components. Did you mean they're not necessarily disconnected components, or could there be an edge present in DFS that it's not?
No, so there's all these edges that I've drawn have to be in the graph. By the way, connected component, I'm not sure what disconnected component, but connected component is like a bunch of things that are all connected. My point is, okay, I think I understand. What you're saying is that it's not necessarily the case that these two trees that I've drawn have no edge between them. You can have edges between them, right? But the edges will always go from one component to the other, right? And how could this happen? How could this happen in the graph? Yeah?
I take the root on the left first, and there's no edge from any of the leaves to the other one, so I never...
Exactly. Precisely, right? So maybe when DFS was processing things, it just decided to process this first. It explored all of this, but it had no chance to go there. Exactly. So in DFS, what's important is to look at, so you have these tree edges. And the question is, what do the other edges of the graph look like? Right? So there are a bunch of other edges in the graph, and we're going to give them a definition. We're going to call them something depending on how they behave with respect to this tree. So you have edges like this. You could also have an edge like that, which is within the same tree, going from a node to its descendant. And you could also have an edge like that, going from a descendant to an ancestor. Or you can also have edges that are like maybe just going across from that to that. Right? So you could have all these possible. Yes?
One on the right, where you made the second dotted line just now, couldn't you not do that? To the right of it?
That.
No, yeah. Couldn't you not do that because each node can only have one parent?
So each node is only one pair. These are edges of the graph. So what I'm dotting are the edges in the graph, not edges that are part of the predecessor or the DFS forest. So in the forest, you're right. Every node has exactly one parent. But in the graph, you could have all kinds of other things going on. Does that answer your question? Okay. So what happens is DFS started there, decided to explore that, then decided to explore this, then backtracked, explored this, backtracked, explored this and this. Right? So maybe this edge was there, but DFS just didn't bother. By the time it looked at this edge, this was already visited. So it never had to actually use that edge in the predecessor structure. So these have names. So this edge over here that I drew. Okay, so this is called a back edge. It's one that goes from descendant to ancestor. This edge that I drew over here is a back edge. Yeah? Question? No? Clear? This edge that I drew over here is called a forward edge. It's from ancestor to descendant. And these are actually called cross edges. That's a cross edge. Cross edge. And these are called tree edges. So sorry, this picture is getting a little messy. But you'll see that there are basically four kinds of edges. There's the tree edges, which DFS discovered. Then there are the back edges, forward edges, and the cross edges. Now, all of these depend on how DFS was done, the ordering, like the labels of the vertices. Yeah.
The back edge in the graph introduces a cycle.
Is that?
It introduces a cycle.
Okay, you're getting ahead. Yes. Yeah. Okay, so the picture wasn't that bad then. Yeah.
What is the definition of
Cross edge. So cross edge is basically anything that is not a tree edge, not a back edge, and not a forward edge. Just everything else. It doesn't connect an ancestor and descendant. That's a cross edge. And they're not that important, but I'm just showing that they're also there. Somebody said something, yeah.
So you can form a cross edge where the two trees are not connected in your DFS, but theoretically are connected in your TM.
Yeah.
It is a directed graph, not a undirected.
Good point. Right, exactly. If it was undirected, then the only cross edges would be within the tree. You could have, this is also called a cross edge.
Sure, yeah.
But this won't exist. Good observation. By the way, so the thing is, a lot of I'll say this because you're here. My midterm and final questions will often be questions of that form. Like observations on cross edges and tree edges. So it's useful to think about these, look at this picture and understand what are the different kinds of edges. Yeah?
Could you define a cross edge as something that goes between ancestors or between descendants of the same generation?
Not necessarily, because this is a cross edge. It doesn't go between, it's just different trees. They're not descendants of any common thing.
But if they're two ancestors, that is kind of the same generation. Because you could think of two ancestors.
Well, you could also have this.
That wouldn't be a forward edge?
That would not be a forward edge because, yeah? Exactly. So anything that connects two vertices in different trees would be a cross edge. But it could also connect something in the same tree, but not an ancestor or descendant. Okay? So these are the different kinds of edges. Okay, good. So I will keep this picture here. And so now I will ask a question. Can the DFS forest of a DAG have a back edge? And so, is it yes, no, maybe not? So I'll let you, I have the picture up, and my question is, can the DFS forest of a DAG have a back edge? That's the question. So well, you can talk or whatever. I'll give you a few minutes to ponder about this and ponder on that and give me the answer. In case you. But don't lose these. I'm running low. My stock of Post-its is going down. Okay. All right. So what is the answer? Okay. I think most of you given the correct answer. No. Why? I think it was pretty much answered, but still, let's hear the answer again. Yeah? There is an example. What does that example tell you? It introduced cycle, but I think the example could be a maybe, maybe not. But you're right. Essentially, whenever you have a back edge, you have a directed cycle, because you always have, so what does a back edge do? So this is a back edge. So that means that U is an ancestor of V. So what does it mean for U to be just a second, U to be an ancestor of V? In the tree, you must have this, right? The tree edges give you a path from U to V, and the back edge gives you a path back from V to U, and that's a directed cycle. Yeah?
I think it's maybe, maybe not if you have cross edges.
Oh, you mean can it have cross edges? Yeah, that's a maybe, maybe not. And even the other, forward edges, is a maybe, maybe not. But back edge, exactly, right. So this is kind of interesting. It's like you just run a DFS, and if you find a back edge, you know it's not a DAG. The big question is does the converse hold? So what is the converse? So I just make a statement. My statement is, I'll just write this down. If G is a DAG, then no DFS forest of G has a back edge. Right? That's the statement. What is the converse of this statement? So this is a little careful. Yeah?
If G has a back edge, then it's, or sorry, if the DFS force has a back edge, G can't be a DAG.
That is actually equivalent. It's the same statement. Basically, was P implies Q, and you said not Q implies not P. Yeah?
So you're saying if there is no back edge, it must be a DAG.
Exactly. I'm saying if there is no back edge, then it's a DAG. That's not at all obvious. Why? Why is it not obvious? So here's my DFS forest. Maybe there's a cycle in the cross edges. Who knows? Yeah?
That statement just disregards the other edges. Like, it just assumes that other edges can't make the cycle.
Yeah, exactly. So what I'm saying, so the converse, so this was an easy fact. We just argued, and it's pretty easy to see. The converse and I'll state this kind of carefully. I'll say if okay, so let me write this carefully. I'll say fix a graph G. What happens is that for any DFS forest, if the forest does not have a back edge, G is a DAG. So what I'm making, and I'm claiming this is true, I'll show you why this is true. What I'm saying is, consider any DFS forest. If the DFS forest does not have a back edge, the graph is a DAG. So what I'm saying is, the cross edges by themselves are not going to form a cycle. Like if they form a cycle, then somehow there's going to be a back edge. Okay, that's the statement I'm making, and I'm going to show that this is true. And then once this is true, you'll see why you have a linear time algorithm. You just run DFS and you just check all the edges to check if they're back edges. Is that clear? Yeah. Yeah? Yes. It's always the case. It's always the case. That's why I said fix a graph for, maybe I should say for all graphs. So I'll say, let me write this differently. For all directed graphs G. For all directed graphs D, for any DFS forest of that tree, if the forest doesn't have a back edge, then it's a DAG. Yeah?
Can you re-explain what you said by the cross edges?
Forming a cycle? Sure. Okay. So, now what could happen, right? So, is how do you know? So you've got, let's say you have this DFS tree over here. Now, I give you the statement. And the first thing you should say is like, but why should that be true? Because maybe the cross edges, which are like going like that, sorry, I'm just going to circle the cross edges. Maybe this thing forms a cycle. The cross edges will the cross edges with some of the tree edges and some other edges could like come together and form a cycle. How do you know that's not going to happen? So that's my point. So the claim is if you run DFS, another way of saying this, if you run DFS on something that has a cycle, you'll always find a cycle that involves a back edge. Like somehow DFS cannot be fooled. It's always going to somehow find a cycle with a back edge. Yeah?
Could you say that there are no cross edges in the DFS forest?
No, there are cross edges, but they'll never come together and form a cycle if it's a DAG. The other way around. The thing is, the easiest way to state it is this. If there's no back edge, it's a DAG. Which means that if there's no back edge, then it is also true that the cross edges together with the tree edges cannot form a cycle. Just by the fact that there's no back edge. Sorry, there's a hand up there and then you. Yes?
In the example that you drew on the right,
that huge mess, yeah.
Yeah. Are any of those considered back edges in the?
So, no, none of these were back edge. This may have been a back edge. But I could redraw the example so that, okay, so let me redraw the example differently. So,
And then is there a proof that says the DFS will always find the back?
yeah, I'll give you the proof. Yes, there is a proof. Yeah.
Is it because even like in the example that you drew, like the messier one, like that, the one that's right by your finger, and then the way that it goes up, because it goes up to a different ancestor, it's gonna come out at a different point. Therefore, it's like not actually like a loop. Like it's like going through like a different path, but it's not actually looping back into itself because it doesn't loop into its own ancestor. If that makes sense. Therefore, that like, because like this looks like it could be a cycle, but it's not a cycle because it doesn't ever actually.
No, but like this.
Yeah.
This could have, like, why doesn't this happen in DFS? Which is that I'm just looking at all of these 4 leaves, and maybe there are like cross edges amongst them. Someone else had your hand. Yeah, yeah.
Maybe once you reach the loop, you will go around the loop because you're looking at everything there.
So yeah, essentially the thing is that like something like that can't happen because DFS, as soon as it hits the first leaf, is going to start discovering everything else. But I'll make this formal. I'll give you like a very nice, clean proof of this, which will convince you, and we'll just use the parentheses theorem. It'll be pretty straightforward. Yeah. So the problem with the term connected component is that connected component makes more sense when it's undirected. When it's directed, it's a bit complicated, right? Because you have, you could have multiple trees even though there's only one connected component or one. So for example, you could have, just as we discussed over here, you could have something like this. Suppose your graph was like this. If you decided to start DFS from here, you would only get one tree.
I'm just having trouble visualizing. Do you think you can give me an example
Of?
there's only one connected component. All of the nodes are connected, but still we can have multiple trees.
Okay, all right, I'll give you an example. Well, this is the example. Smaller example.
Next to the graph.
This is the graph.
I think this is the forest.
No, so I've actually, the forest are all the dark edges, the dotted ones. Let me draw it separately. That's fine. So imagine that there's just, yeah, okay, I've run out of ink. I have a spare. Okay. Actually, I have many spares, but okay. So suppose my graph looks something like this. And just to make it interesting, I'll put 3 sort of connected-ish components. And so this is a directed graph. And that's a directed graph. And this is some directed graph. Let me not worry too much about what's happening in here. But suppose what you have is from here, you have one edge that goes back there. And from here, you have one edge that goes back there. And there are no other edges between them. Now, if DFS were to start here, you'll get one, let's say, maybe you'll get one tree. Because this, potentially, let's say it explores everything here, it'll go there, explore everything there, and explore everything there. But if you start DFS here, you get one little tree for this. And then you'll go here, let's say, at some point. But this is already visited. So you don't even go down that path, and then you'll form one tree for that, and then you get one tree for this.
So because we are running DFS on every vertex.
You're running DFS on the whole graph, right? So you loop over the whole, exactly, yeah. Is that clear? Is that it? Okay, good. Okay, so let me prove to you this converse. Let me prove the converse. That if it does not have a back edge, it must be a DAG. Okay? So this actually is a little trickier to prove. Which is actually why it's in your homework. So, but I'm going to tell you how you're going to approach this question. Okay, and I'll sort of verbally explain it to you, and then you need to write down the proof. Okay, so what you kind of saw was that the reason why this doesn't happen is that as soon as you discover like the first leaf, somehow you'll end up discovering everything else, and somehow that should lead to a back edge. That's the argument. So for this, I actually need to prove another theorem for you, and then, which is also part of the homework. But then once you have those pieces, you'll be able to show it. So the theorem that I'm first going to give is something called the unvisited path theorem. So what does the unvisited path theorem say? It says, consider the time when U is visited. Right? So as you're running DFS, there's some U and it gets visited at some point. So let's look at what happens at that point, at that time. If there is a path of unvisited neighbors from U to V. So at the time that U is visited, there is some other V somewhere, and there is a path that is all unvisited. Does this make sense? Then V is a descendant of U in the DFS forest. Okay, so what is this saying? It says, suppose there is some path of unvisited vertices from U to V, then it is guaranteed that V is going to be a descendant of U. That's what the statement is saying. Okay? Okay, so we're about 50 minutes, so let's take a break for about 3-4 minutes, and then we'll reconvene and finish this argument. Okay, all right. Let's continue. So the main tool that you need to prove this converse is that if any DFS forest, if D does not have a back edge, G is a DAG, or at least I think it's in the homework. Now I've forgotten, but anyway, is you need this theorem called the unvisited path theorem. So the unvisited path theorem says consider the time when U is visited. If there is a path of unvisited neighbors from U to V, then V is a descendant of U. Okay? So how do you prove this? So this, I'm pretty sure, is in the homework. So to prove this, I'll actually prove a simpler statement, and we'll actually prove it, and then you just need to do sort of some induction on it, and you'll see that it's... So I'm going to prove something which I refer to as a claim. A claim is usually like a smaller statement to prove. And this is the simple case, which I'll call the unvisited neighbor theorem. So what is the unvisited neighbor theorem? It says, again, consider the time when U is visited if there is a neighbor V of U that is unvisited, then V is a descendant of U in the DFS forest. So I'll show you why this is true. The proof of the unvisited path theorem is basically induction on this. You use this statement. So you can use this statement for your homework, and you do induction, and you can prove that. So it's a good exercise in an induction proof, which is why I've given it to you as part of the homework. Now let me explain why this is true. I'm not saying that U is a child. It might not be a child. It's just a descendant. Okay, so let's see why this is the case. So consider the situation of this theorem. Right? Consider the situation of this theorem. So here is U and V. There's an edge between them, right? Because I said that it's a neighbor. And so by neighbor, I usually mean like out neighbor, right? So path is always in the directed graph. So the first question is the discovery of U less than the discovery of V? Is it yes, no, and by maybe? Maybe is like maybe, maybe not. So again, consider the situation in this theorem. U and V as given in this in the claim. Is this true or not? We are proving the claim. We're not assuming the claim. We are proving the claim. Is discovery of U less than the discovery of V? Give you a couple minutes. Okay, what is the answer? Okay, I guess maybe you need a little bit more time, but I think most of you see that the answer is yes. Why is the answer yes? Why is the answer yes? Anyone? Yeah?
Because you just visited U and V is unvisited.
Exactly. So it's just by definition, right? It's like U has been visited and V is unvisited. Okay, now the harder question is the finish time of U less than the finish time of V? Is it yes, no, maybe? So think a little carefully about this question. Okay, what is the answer? It's a bit more mixed. So okay, maybe I won't even tell you what the answer is. So does anyone want to explain why they gave the answer they gave? Yeah. What do you say the answer is?
I thought it was what we're sharing, but I think it's no. I think finish time of view has to be less because of the parentheses.
You mean the finish time of view has to be more? If you said no.
Oh, wait, never mind. Okay, well then I guess I'm saying yes.
Okay, then you're saying yes. All right. Okay, that.
When you first discover you open that first.
Okay, good. So let me draw that. So you're saying I first open the discovery of U parentheses.
Actually, I was thinking about it backwards. But you first discover U, then you discover V, and you have to close the V bracket before you close the U parentheses.
Why?
Because you told us.
Huh? No, the parentheses theorem doesn't say this has to close first. It could also close later and look like that.
Yeah, that's what I meant.
This one.
Yeah, I meant the bracket has to close before the the inner one has to close before the outer.
The inner one has to close before the outer one. So what is the answer going to be then? No. Why should the inner one close before the outer one? Okay, good. All right. Yeah.
The nature of the stack where if you hit the square bracket, that gets completed, and then only the regular
Why?
handle.
Because remember, the parentheses theorem says, so you guys are sort of on the right track. It could look like this also. Or it could look like this. Yeah, you had it.
U can only be finished after it has visited all of its unvisited descendants. And so V will have to finish all of its.
Almost.
Before U is finished is kind of what
No, you're on the right track. There's a much more direct way of saying what you're trying to say. Okay, so I'm going to sort of, I think maybe it's useful to also have the DFS code up there just so that, someone else, yes.
in the second case of the parenthesis,
This one?
both sides.
This one.
Yeah. Does that mean that U and V are not connected?
Well, I don't know. I mean, they could have, you don't know. All you know is that the discovery and finish times are like that. The parentheses theorem tells you nothing about connectivity. It just says, this is what the discovery and finish times look like.
Doesn't it say that they're not descendants of each other? Or they're not?
It would say that in this case, the inner one is a descendant of the outer one. Yes, you're right. That it also says that in that case, neither one is a descendant ancestor in the forest, but in the graph, you don't know how they're connected. Yes?
But since you have mentioned that there exists an unvisited path between U and
No, it's just a neighbor in this case, right? This is the unvisited neighbor theorem.
okay, and since then V is bound to be explored
Why?
since it's the unvisited neighbor.
But it's the unvisited when this is visited, but this has got many neighbors, and it's going to go through those neighbors.
Eventually, it can happen that U's neighbors will also at some point, maybe in such a case that they can lead to V. In that case, also V will get explored, then it will backtrack to U.
Right. So I would say this even more directly, right? Look at this for loop. So at some point, what is the for loop going to do? It's going to look at U. It's going to look at V. At that point, either visited, I guess actually technically the U and V are, it should be S and U, but you know what I mean. My point is, look at the for loop from U. At some point, it's going to process this neighbor. If the neighbor is already visited, well, then you're in this situation because U still hasn't finished. And if it's not visited, well, then it's going to visit at that point. It's clear? The point is that U will check its neighbor V at some point in the loop. At that point, either V is unvisited, in which case it's going to visit it, or it's already visited. But in either case, the visit of U happens before U finishes, which is basically what all of you are sort of saying, just restating that. I'll write this down a little bit more clearly. Okay, so is the reasoning clear? Yes, no, you don't seem very convinced. Yeah? Let me write. I'll write and then you can question me. Okay? So I'm just going to write out the proof of this theorem. I'll say we argued that discovery of U is less than the discovery of V. Sure, that we did over here. Now let us show that, so this is sort of the important point, is that the finish of V is less than the finish of U, which means we're going to be in this situation. So I'll say in the for loop over U's neighbors. Yeah? Is unanswered yet? Yeah? No? Okay, all right. In the for loop over U's neighbors, V will be processed. Right? So at this point, U has not finished. So basically there are two cases. At this point, V is unvisited. So if V is unvisited, then what's going to happen is that V will get visited. So, I'll write this down, is that the discovery of U is going to be less than the discovery of V, which we know, is also going to be less than the finish of V, because V got visited before U finished. Right? So what this is saying is the picture looks like this. This is the discovery of U. This is the finish of U. This is the finish of U. And the discovery must have happened somewhere in between. And so by parentheses theorem, you have this. That is that the finish of V is before the finish of U. Right? So if it's unvisited, it's going to visit at that point, but obviously the visit is while U is running. So by parentheses theorem, we're done. So case 2 is V is visited in the for loop. But in this case also, what this means is that the discovery of U is less than the discovery of V. And this we know. And obviously this got discovered at some point before this got finished. Again. Yes?
When you say the parentheses theorem, shouldn't it be finish V is less than
Thank you.
If V is already visited when you're looping through use neighbor, doesn't mean that mean discovery of V was before discovery of U?
No, good. So we started off, remember when we start off, we have this, right? This is by assumption. When U was visited, V was unvisited. Good, right? That's why I need that. But I'm just saying when you looked at U, it got visited at some point. You don't know exactly when, but you know it's in between those times. And so again, the picture looks like this. Right? So what this means is you have discovery of U, finish of U, and the discovery of V happens somewhere in between. Yes? Okay.
Started with that pre-concept that U was visited and V was unvisited.
Correct.
And I understand the first case that you made, but second case, then I'm
So V is visited when U looks at V. Remember, in the for loop over U's neighbors, at that point you're seeing what's happening. So there are two situations. Right? One is initially, as soon as U is visited. That's what the precondition was. In the proof, I'm looking at the situation when the for loop actually processes V. Because there's a for loop over all the neighbors.
So we are considering the discovery of V as like a local thing or like a global discovery?
There's no local global. There's at some point there's a timestamp set for its discovery.
But if it was already visited, wouldn't the discovery time of it would be before?
It was discovered after U was discovered, though.
But then wouldn't it be just unvisited? If V wouldn't it be unvisited if
No, so let me give you an example. So let's just say that there is an edge from here to here. And so what U did was process neighbors in this order. So it visits this, backtracks, visits this, finishes. Then it visits this. Now this is eventually going to lead to this being visited. So it's going to backtrack. So then U is still going to look at all of its neighbors.
But what if someone else already visited?
Visited U, V? But you know that it happened after the discovery of U. And this is by the precondition of the theorem.
Okay. In that
Right? Basically, it's you just say that this must happen. That's it. And then you invoke the parentheses theorem. Go and stare at it. Like, yes. It's not something that you can internalize in 5 minutes. You can kind of see it. You have to go back and look at it. So in this case, you also have this, and then by parentheses theorem, done. Yeah.
I'm a little confused about the difference between these cases.
There's actually no difference. The difference is just that the reason I broke it out is to just say that when U is looking at the neighbor V, at that point V may be visited or unvisited. Like it could be that there's some other child that led to it, or maybe not. But regardless of those cases, the same situation happens.
So one of the cases it's already visited.
It's already visited in between.
So which one is which? So the first one is you actually visited
As a child,
as a child, and the second one is got visited with.
through some other path. I mean, the reason I'm just breaking this is to show you that these things, you actually don't even have to write it this way. Okay? So what this gives you is the unvisited neighbor theorem. You have to do induction on this to get the unvisited path theorem. Okay? But what we really cared about was all this stuff about DAGs. And where is all of this relevant there? Okay? What we really cared about is this statement. So what I'm now going to show you is if the unvisited path theorem is true, then you can actually show this. Okay, so I'm going to sort of chain these things together. That I'm not going to write out in its full glory because I think it's on the homework, but I don't remember. So if it's not on the homework, then I might just write it out and send it to you. And if it is, then I won't. Okay. All right. So you have this unvisited neighbor theorem, which we just discussed. From that, you use this plus induction to prove this statement. This is part of the homework. So what this says is when U is visited, if there is a path of unvisited neighbors from U to V, then V is a descendant of U in the DFS forest. Okay? Now using this, I'm going to now show what I'm going to show you is, suppose G is not a DAG, then some edge becomes a back edge. Right, this is what I need to show you, right? Which is equivalent to saying that if there is no back edge, then it must be a DAG. Okay? So why is this the case? So I'm just going to draw out this picture. I'm not going to write out the proof in full detail, but hopefully the pictures will explain what's going on. So what this means is there's some directed cycle somewhere. Okay? So look at this directed cycle. And what you know is that at some point, one of these vertices is going to be visited for the first time. So consider some point, so at some point, one of these vertices is visited, I should say, for the first time. Call this U. Okay? Yeah? That's because of the for loop of the DFS, right? Not the for loop of the neighbors, but the for loop over everything. Because it's going to loop over all the vertices. At some point, everything is visited. I claim that if you just invoke the unvisited path theorem, you'll finish the proof. Why? So at this point, U is the first vertex that got visited. What can you say about all the other vertices on this cycle? They're unvisited. Yeah?
You're going to somehow not end up closing U before the parentheses.
Don't even worry about the parentheses theorem. You don't even have to go that far. Just use the unvisited path theorem. It's 2 sentences. This is the proof, yeah?
Because you right now is being visited, the rest are unvisited. With that, all of those will be descendants of
Exactly. So everybody on this cycle is going to be a descendant.
and but eventually
That last edge is a back edge. That's it. Yeah?
Could you also say that U is a descendant of U? Maybe? And then that would be the
Well, U is not a descendant because in the tree structure, it's pretty fixed. U is a parent and everybody else is a descendant. It's just a back edge that's going to form. Right? The back edges don't give you... So the ancestor-descendant relationship is based on the tree edges, not on the other edges. Does that make sense? Yeah. Okay. So all I'm saying is, I'll say this, maybe I will write it. By the unvisited path theorem, because at this point, U is visited, there is a path of unvisited vertices to V, who is the previous guy on the cycle. It's not the predecessor, it's the previous guy on the cycle. There is a path of unvisited vertices. So V is going to be a descendant of U, which means that edge, VU, is a back edge. That's it. That's the proof. So now you know that actually if G is not a DAG, you'll always find a back edge. It's kind of remarkable how you stitch these things together. It's very hard to visualize what DFS is doing if you think about it in terms of, oh, there's a recursion and there's this backtracking and all of that. So what these arguments help you do is to sort of encapsulate those in sort of whatever, formal ways, and you can argue about it more easily. Does this make sense? So I'll write this. So take V, the previous vertex on the cycle, there is a path of unvisited vertices from U to V. So V is a descendant of U. So the edge VU is a back edge, and that's it. Okay, actually I wrote the proof, so if it's actually in the homework, then you just go ahead and copy this and get 2 points for free. It's fine, right? Does that make sense? So you have to build, you start with the unvisited neighbor theorem. Actually, you start with the parentheses theorem, which you show. Then you have the unvisited neighbor theorem. From there, you get the unvisited path theorem. And then from there, you prove the statement, this converse statement, that for any DFS forest, if it does not have a back edge, it's a DAG. Because if it's not a DAG, there will be a back edge. Sorry? So it would actually be, it depends on who is the first of these that got visited. So if this was the first that got visited, then that one becomes a back edge. So it all depends on the time, and this is where you don't know which of those becomes a back edge because of the labeling, but you know there will be some back edge. Yeah?
This may be a stupid question, but how will a DFS forest ever have a back edge? Because when you come back to when you find that your descendant is your ancestor in a cycle, wouldn't you never form that edge in the forest? Because
You wouldn't put the edge in the forest. The back edge is not a forest edge. It's an edge of the graph.
Okay, cool.
Right? So the tree edges don't form a cycle. The tree edges are like the predecessor edges. The back edge is an edge of the graph. Got it? Okay, good. Okay. So once, this is, it takes some time to sort of internalize all of this. But once you put all these pieces together, the topological sort question actually becomes pretty easy. Okay? So at this point, so actually someone on Zoom asked me to put page numbers on this, which I should. So I'm going to start with page numbers now. It's a bit late, but whatever. Okay, so this is page 1, I guess. Okay, and then from now on, I will start putting page numbers. Actually, I don't know if you want me to put on Zoom, like they want me to put page numbers of everything, so it'll be like number 50 or 60. Yeah, I could make them negative. This is too much work for me. So, okay, all right. So what we have right now, what I have shown to you, is this fundamental fact. This you need to know. Given the adjacency list of G, determine if G is a DAG. Even if you have taken nothing away from today's lecture, you should be able to say this. That yes, if you run DFS, there's a linear time algorithm to determine if it's a DAG, and that's by finding a back edge. If you do this, then if you ever get caught in an interview and they ask some question about this, at least you'll say that, and they'll say, okay, fine, you know that. This is like a fundamental fact you need to know. Okay? It's a fundamental graph algorithms fact. Now, how do we do topological sort? And since you've been thinking about all these questions, I'm going to ask you a series of 3 questions, and by the time you answer that, you'll see how to topologically sort. So suppose G is a DAG. Right? So you actually have a DAG. And then you want to sort of order the vertices. I'm going to show you that you just use the finish times and you can actually get that ordering. So how? So suppose there's an edge UV. Question: is the discovery time of U less than the discovery time of V? Yes, no, maybe, maybe not. Okay, good. So most of you are saying that it's maybe, maybe not, which is right, because you don't know. Maybe it decided to visit U first, and if it visited U first, then it's going to visit V. It's going to discover U and V. But it could also happen that just by the loop, it sort of looked at V first. Okay? Now the harder question, the more difficult question, is the finish time of U less than the finish time of V? Okay, this is a trickier question. So I'm going to break this up into two cases just so that we understand. So I'll just say case one. Suppose the discovery of U was less than the discovery of V. Right? So suppose we're in the situation that is U and this is V. Right? Suppose this is what happened. Yes, no, maybe. What's going to happen? Yeah? Okay, so what is going to happen? Mostly, I see blues, no. Why? It's basically this unvisited neighbor theory we just discussed, right? We said that U was discovered first, so V was undiscovered, right? And so you're going to have this situation. And so what we got in this situation is no. Now case two, suppose the discovery of U was after the discovery of V. So the situation you have is that's V and this is U. Now is it yes, no, maybe? The hint, I'm giving you a hint, is remember, suppose G is a DAG. Suppose G is a DAG. Now what is the answer? Yeah, okay, what's the answer? It's more tentative. There are a bunch of most somewhat no's. Why?
Because it's a DAG, V has no connection to U.
V has no path back to U.
So V has to, the square parentheses has to finish before the open parentheses.
Because if the square ended over there, then by the parentheses theorem, U is going to be a descendant of V, but it's a DAG. U cannot be a descendant of V. Right? So the answer again is no. So it must look like this, because U cannot be a descendant of V. You should now be able to tell me how to topologically sort. What do you do? So look at that edge. So if there's this edge UV, then what you get is that the finish of U is more than the finish of V. Right? That's what we just argued. If G is a DAG, If you have an edge, the finish of U is more than the finish of V. So V will always finish later. How do you topologically sort now? I know, 5 minutes are left, caffeine is down. Neurons have stopped firing, yeah.
Any vertex that has a finish time greater than some other vertex
Yeah.
you processed before, or basically that's how you decide the order.
So what is the ordering? Yes?
You sort by finish time.
In decreasing order. So you just sort by decreasing order of finish time, and that's a topological sort. It's beautiful, right? You run DFS once, you check if there's a back edge. If there's no back edge, you know it's a DAG, and then you just take the finish times, you do reverse order of finish times, and that's a topological ordering. Yeah?
Could you also do a graph traversal to get topological ordering?
Well, this is a graph traversal because DFS is traversing the graph, so. But the point is, the reason why this is so quick and easy, right, is that you don't really have to modify the graph in any way. You don't have to like remove something from the graph, change the edges, and do something else. It's just really transparent. Well, it's transparent in terms of the code. It's opaque in terms of why it's true, but now you know why it's true. So I'll write this down formally, right? I'm just saying the reverse order of finish times is a topological ordering. Okay? And this you can compute in O of m plus n time in a single depth first search. Okay? So this is how you do topological sorting. Technically, you don't really go and sort those numbers because that would give you n log n to sort. You can kind of, actually every time you finish, you can just sort of like append, you just push it in front of in a list. Right, actually, no, the other way around. So you can just create a stack. Like every time you finish something, you just push it on top of a stack. And you keep doing this, in the end, the stack will give you the topological ordering, right? So just as a comment, don't sort by finish times. That would take O of n log n. Instead, when a vertex finishes, you push onto a stack, and then the stack at the end gives a topological ordering. Okay? Yes?
Topological sort would be useful in terms of compilers, in like what to compile.
Exactly. So you could just use this ordering. You just have a stack, and then you compile in that order. So any sort of processing of a scheduled processing where you have dependencies, you would use this to do it. Yeah? Okay. So we're basically done. We have 1 minute. I just want to say there are two fundamental facts you have to remember. The rest of it, if you forget, well, bad for you. But still, what you need to remember is the way to find a DAG is you run DFS, look for back edges. The way you topologically sort is reverse order of finish times. These are the two fundamental facts you should remember from today. I will ask you other things on the test,